is called the Fundamental Theorem of Calculus. So we're going to take antiderivatives and integrals even further now. So purpose. The Fundamental Theorem of Calculus enables us to compute integrals by using an antiderivative of the integrand function rather than by taking limits of Riemann sums. Right? So we're trying to avoid Riemann sums here, which is what we did in 5.2 and 5.3. You guys love that, I know. Even though you were in here, I still know that you love that section. You know, building all those rectangles and then doing infinitely many rectangles by taking the limit. Oh yeah, so much fun. Alright, definition. If f of t is an integrable function over an interval I, then we can define a new function. This guy right here. Now, up until now, on the right-hand side here, this would have been a Riemann sum. But what we are going to be doing is getting rid of the Riemann sum and using a different technique. So, alright, what is this? Alright, after we get to what you've already learned. So let's suppose f is a positive function. So, what is this? Okay, so let's suppose my f function is this guy right here. This is my f of t. And this is the t-axis, and this is the y-axis. Alright, so when I say integrate f of t from a to x, let's say this is a and this is x. What is this integral actually getting for me? Remember, this integral notation is really the same as the Riemann sum. It says, find the area under this curve. This is what that integral is trying to find. The difference is that we don't have a fixed value for x. X is changing. So if x moved a little bit to the right, over here with x, then our area would include this area as well. So this is why it's defined as f of x, capital F of x. It is the antiderivative evaluated at however far along you went. So think of this as the area under the curve from A all the way to x. X is moving. Because the x is moving, that's why this is still a function. It's not a fixed number when you integrate because it depends on where x is at. Alright, that was a little bit confusing, but just get the idea. That's the main thing. I'll show you how to use it. So here's the theorem we want to use, so we're going to apply it to that function we just defined. If little f is continuous on our interval, then big F, integral from a to x of little f, that one we just defined, is also continuous. So the area under the curve, no matter where our x is, those values are going to be continuous values. No matter what x you pick, you're always going to end up with a function, capital F, that is a continuous curve as well. If you were to graph the areas, anyway, I'm doing 2D and I don't need to. Alright, so the capital F is continuous and also differentiable, and its derivative is little f. Okay, so we're taking the function we just defined, and now we're taking the derivative of it. You take the derivative of the integral. What do you get? Little f of x. Well, that's cool. What does it say? It's saying you take the x you have in your upper limit of integration, and you plug it in. That's your answer. The derivative of the integral is just evaluating little f at that upper limit x value. Let me show you. Oh yeah, we will call capital F an antiderivative of f of x. Not the only one, an antiderivative. So use the fundamental theorem we just talked about to find dy dx. So we have y here, and we want to take the derivative of it. Notice, y is an integral. We want to take the derivative of the integral, so we apply the fundamental theorem. Because this function that we have here is continuous and differentiable, capital F will also be continuous and differentiable. So dy dx, what you're going to do is you are simply going to take the x in the upper limit of integration, and you're going to plug it in wherever there was a t. dy dx is equal to, instead of t squared, x squared. Instead of 2t, 2x. There you go. Don't you like it? You're probably thinking this is too easy. Hang in there. It's okay. Some things can be easy, but it will get more interesting. You're right. For example, what is wrong with this problem? Why does the fundamental theorem not apply to this problem? Cosine is continuous, cosine is differentiable, that's not a problem. The issue is the limits of integration. What's wrong with this? Go back and compare it to our fundamental theorem of calculus definition. Right here. What is wrong with our limits of integration? Fundamental Theorem of Calculus says your lower limit has to be a, fixed value. Your upper limit is where the x should be. So because of that, fundamental theorem doesn't apply. Or does it? Didn't we talk about something we can do to switch our limits of integration? If we switch our limits of integration, put the 3 at the bottom and the x at the top, what else do we have to do to our integral? Put a negative out front. Very good. Excuse me. To switch your limits of integration, you have to change the sign of the integral. Alright, now fundamental theorem of calculus can apply. If we want to find dy dx, we take the derivative of the integral, the negative is still going to be there. Negative in front, he hangs out. What you have to do is take your x and plug it into the function inside of the integral, wherever there was a t. Instead of cosine of t, we have cosine of x. Cool. Alright. Ready? Here we go. Oh boy. There's something else that's not quite right here. What's wrong with this picture? Well, our limits of integration are in the right order, but the fundamental theorem of calculus only defines if we have just x up top. We don't have just x up top in this new example, we have an x squared. So what are we going to do? Okay, so what we're going to do is we're still going to do dy dx. Now, I'm going to do this the easiest way possible to avoid confusing you. Basically, what you're going to do is you're going to do chain rule. Easy enough? So, you're going to take sine of t as your inside. No, wait. No. All the way. Sine of t is your outside, because x squared is going into that. X squared is your inside. So the chain rule says you take the derivative of the outside first. So that's going to be derivative of sine. No, I'm going to confuse y'all. Hold up. Easy. First time we're going to do this the full way out. That's what we're going to do. We're going to do this the way. Alright. I'm going to do it the long way and then I'll shorten it for you a little bit. Alright, so to find dy dx, what we're going to do is we're actually going to rewrite this problem by getting rid of x squared. We're going to integrate from 2 to maybe u. Done for you sub already, so you should understand that concept. What I just did was I said u is equal to x squared. So then we have sine of t. The problem is, if I take the derivative of this integral, it's not going to be dy dx. I don't have an x anymore, I have a u. The derivative of this integral is going to be dy du. Now, big chain rule. How do we get back to dy dx if we have dy u? Just multiply by the derivative of u, which would be the derivative with respect to x, because u is a function of x. Hang there for the long way, it'll shorten a minute. So the derivative of the integral, well, that is just the fundamental theorem. We take our u, we plug it in. No derivative or anything, just take the u and plug it in. The derivative and the integral basically cancel out. We end up with sine of u times du dx. Well, u is right here. What's the derivative of u? 2x. So we have sine of, well, u is just x squared times 2x. There you go. That's not so bad, right? Now, basically what just happened here. What you're going to do is you're going to take whatever's at the top and plug it in. So dy dx is just whatever was inside at the top plugged in times the derivative of the inside. That's the part you have to get. So you don't have to do all of this chain rule notation. What you have to do is have the x function at the upper limit. Make sure it's from a number up to an x function. Plug that function inside of the function in the integral. Multiply by the derivative of that upper limit. And that's it. 2 different ways to get this. Recommend the short way. That's up to y'all. Alright, I want you to pause and try it, what we just did, and see if you can figure this out. Pause it, come back, and I'll do it with you. Alright, here we go. So, short way. Derivative of y with respect to x. Well, the inside is just 3t squared. Instead of t, we plug in our function. So we need sine of x plugged into the t, don't forget the square. But you're not done. You still need the derivative of what you plugged in. So the derivative of sine is cosine. If you want to write it a little bit shorter, you do 3 sine